Good morning, all of you, and welcome to the second day of our National Mathematics Day program. And today we have the program talk on mathematical beauty. So we have a very distinguished guest with us. She is Mrs. Jayashree A. So I'll just introduce her. Mrs. Jayashree A. received her MSc in Pure Mathematics from the Department of Mathematics, Calicut University campus in 2004 and B.Ed in Mathematics from Farouk Training College in 2005. She has been in the teaching profession for the last 16 years. Presently, she is the head of department in the Department of Applied Science and Humanities at KMCT College of Engineering for Women, Kalantur, Calicut. So welcome, madam, and now the dais is yours. You can start your presentation. Madam, can you hear me?
Yes, thank you very much, sir. Thank you very much. Okay. So, very good morning, everyone. I'm very happy to be here to deliver a talk on very interesting topic, mathematics and beauty. So, first of all, I take this opportunity to thank Mr. Jayantan sir, the Senior Technical Officer and Officer in Charge Innovation Hub, for giving me such a wonderful chance. Thank you very much, sir. Okay, now let us move on to my topic, mathematics and beauty. Okay. See the slide. See the slide. I can't see.
It's fine, ma'am. You can start.
Yes. Okay. So you can see the two words, mathematics and beauty. We can check mathematics in beauty and beauty in mathematics. These two are correlated. First of all, let me ask a question. Can you define mathematics? Can you define mathematics? See, if we ask this question to a student, sometimes they will say, oh, this is a tough subject, right? And some of you may say, it's a subject full of calculations. And some of you will say, mathematics is the science of measurements, quantity and quality. And it's an abstract science. Abstract means a general understanding of science. Or they may say mathematics is the science of logical reasoning. See, actually, there is no generally accepted definition for mathematics. But everywhere we can see mathematics and everything that we do by using mathematics, right? German mathematician Carl Friedrich Gauss, who made significant contribution to many fields of mathematics and science, said that mathematics is the queen of science. Now let us examine the second word, beauty. What is beauty? How do you define beauty? It is actually a quality, right? Or we can say it is aggregate of qualities in a person. Or thing that gives pleasure to our senses, right? So something we say beautiful, if it is nice to look, nice to hear, nice to smell, or to feel, or to think. It's a way an object makes us feel, isn't it? Now let us check the next question. How do you define mathematical beauty? I'm connecting these two words. Mathematical beauty. See, mathematical beauty is the aesthetic pleasure derived from the abstractness, the purity, typically derived from the orderliness of mathematics. So mathematicians express this pleasure by describing mathematics as so beautiful. They also describe mathematics as an art form or a creativity. we can see the joy, the excitement happened in one of the famous Greek mathematician and physicist, astronomer, and an engineer who was known as the father of mathematics. And he has gone down in history as the guy who ran naked through the streets of Syracuse shouting, "Eureka, Eureka." That means, "I have found it." He's none other than Archimedes. See the beauty in the form of pleasure after getting the beautiful result which he has waiting for. Now, another interesting, a beautiful result introduced by Archimedes. It is the area of a circle. Everyone knows it is the area of the circle as pi r square, right? My question is, can you prove this geometrically? There is a very interesting proof for this, the area of a circle. Okay, first of all, we are dividing the circle into different sections. You can see in the picture itself, see in two different colors, yellow and blue. Okay, and you can make this division more finer and arrange this in the below form of a rectangle. See, in the opposite ways you have to join, and you make this in the form of a rectangle. And in this case, the length of the rectangle, this length will be pi r, the circumference. And what about the width, the breadth of this rectangle? The breadth will be r. And we know the area of this rectangle as length into breadth, right? So pi r into r, it is pi r square. So it is a very beautiful proof of the area of a circle. Okay? Now, when we are talking about mathematical beauty, there are actually two different forms: the generic beauty and the exceptional beauty. See, generic means in Malayalam, what we can say, generic means പൊതുവായ beauty, പൊതുവായ സൗന്ദര്യം. And exceptional beauty means അസാധാരണമായിട്ടുള്ള സൗന്ദര്യം. Now let us take the first one, the first type. What is the generic beauty, the general beauty? This is actually the spiritual or heavenly form of beauty reflected in structures or patterns. It's a sense of wonder at the inexorable order in which mathematical word arranges itself. You just think, you can see here how beautifully the natural numbers in a line is arranged. See, the pattern that you can see, it's very nice. And consider the sequence of Euclidean plane of increasing dimension. We have one-dimensional in the form of a straight line, and the two-dimensional and three-dimensional, and so on. These structures are incredibly powerful and useful. And from a certain perspective, this can indeed be very beautiful. But for those on the other side, certainly most non-mathematicians, it's tough to get truly excited, right? Now, let us take the second one. That is exceptional beauty. It's more relatable. And they will focusing on the rules, the proofs, based on new or the original insight. But both these types of beauty have charmed mathematicians over the years and led to many advances. Now, let me ask another question. Is your brain helping you to stay beautiful? Is your brain helping you to stay beautiful? Yes, of course. The brain scanning, see, actually called fMRI. fMRI means the functional magnetic resonance imaging, shows that a complex string of numbers and letters in mathematical formulae can evoke a sense of beauty in our brain. And the same sense of beauty we can see while seeing an artistic piece or a music. The researchers suggest there may be a new neurobiological basis to beauty. Now, I will tell you about certain phenomenon which will happen in our brain, which one looks at beautiful formula or a beautiful artistic piece. You can see the medial orbitofrontal cortex. It is a part of our brain, the medial orbitofrontal cortex. It is a sub-region of ventromedial prefrontal cortex, and many of you know this part of our brain, which is uniquely positioned to regulate the emotions. And it's actually a reinforcer. And neuroscience can't tell you what beauty is, but you find something as beautiful. When you are seeing something as beautiful, this part is likely to be involved. A large area of brain is involved when viewing equations, but when one looks at a formula with a beauty, then the emotional parts will be active. And all these you can see in the fMRI scanning. Okay. Now let me ask another question. Which is the most beautiful equation in mathematics? Which is the most beautiful equation in mathematics? Yeah, it is the Euler equation, the Euler identity. The Euler identity, e raised to pi I plus 1 is equal to 0. It is Euler identity, where E is the Euler number, I is the imaginary unit, and we know the value of I as it is a root of -1, and the pi, it is pi is 22 divided by 7. Now, why this is said to be the most beautiful formula? You can see 3 operations in one single equation. And what are the operations? The addition is there, okay, since we are adding those 2 numbers. And you can see multiplication, pi into I multiplication. And exponentiation also, e raised to. So these 3 operations comes together in a single equation. And you can see only this equation involving these 3 operations together. And also, it links 5 fundamental mathematical constants. You can see 0 there. And 0, it is the additive identity. And the number 1, it is the multiplicative identity. And the number pi, its value, we know it is 3.141 and so on. It is an irrational number, and it is a fundamental mathematical constant in mathematical analysis. The number e, it is 2.718, the Euler number. And the number I, it is the imaginary unit of complex numbers. So that's why this equation is, this identity is said to be the most beautiful the equation in mathematics. Now I'm moving on to one of the famous Greek mathematicians and his beautiful theorem. It is Pythagoras. And the Pythagorean theorem, or you can say Pythagoras theorem, it gives a relation connecting the 3 sides of a right angle triangle. And here you can see the picture. In the blue colored the triangle, a square plus b square is equal to c square, where a is the base, b is the height, and c is the hypotenuse. But instead of giving this as the formula for finding formula gives the length of the sides of this right triangle, this equation not only gives lengths, but the areas also. See, when you're making squares having side A, you make a square, you can see in the other picture, and B, having length B, you may construct another square, and having C, you construct next square. So this theorem gives the area, the concept of area also. How? The sum of the areas of A and B. A square, we know it gives the area of a square. Okay. So A square plus B square means sum of the areas of the first square and the second square. And that sum will be same as the third one, the area of the third square, that is C square. Okay. So this is the beautiful proof of the result of Pythagoras theorem. And Pythagoras worked on a lot of other mathematical ideas, including the working of a guitar. How long the guitar strings need to create certain notes. And this guitar is called Pythagoras guitar. And he found that mathematically, the note's pitch is inversely proportional to the length of the string. That is, frequency increases when the length of the string is decreases. These are inversely proportional. And this is the fundamental mathematics in all the stringed instruments which Pythagoras figured out. Now, whenever we are talking about geometry or shapes, the person that comes in our mind is the father of geometry. That means he is Euclid. And his famous book is The Elements, having 13 volumes. And there are actually 3 sections in this particular book. And they are the plane geometry, arithmetic and number theory, and the solid geometry. And he says that the laws of nature are but the mathematical thoughts of the God. So many years ago, all these beautiful geometrical concepts derived by Euclid, and it is there in the book Elements. And we are following the same today also. Now, if somebody asked you something about it, say something about mathematics, at once we'll recall the formula. What? Yeah, a plus b whole square. And we know the proof, isn't it? So I can see a few students here. A plus b whole square. We know is a square plus 2ab plus b square. It is a square plus 2ab plus b square. How will you prove this geometrically? That is my question. And for that, what you have to take? I'll give you the geometrical proof of a plus b whole square. So for that, first you take a length a. You can see length a in pink color. Length a, first length a. And I'm extending this length to b. Okay, so total length is a plus b. The total length a plus b. And take a plus b as the length. You draw a square. So draw a square having length a plus b. And you just draw 2 perpendicular lines. You can see 2 perpendicular lines. And then it will form 4 different rectangles. In that, you can see 2 squares. And we know area of this, the whole square will be the sum of areas of those 4 portions, areas. And the pink colored one is the area a square. And the 2 green colored rectangles, you can see whose area will be AB each. And another, the small pink colored square is its area is B square. Now you add up all these areas, you will get A square plus AB plus B square, right? So what will be the answer? It is A square plus 2AB plus B square. See the proof of A plus B whole square? So this way we can do any algebraic identities. Okay. And now come to an important and beautiful number that we can say in a sequence, or we can say a sequence. It is Fibonacci numbers. Fibonacci numbers. Or we can say Fibonacci sequence. A sequence of the form, you can see 1, 1, 2, 3, 5, 8, 13, and so on. How these numbers, these sequences are arranged, you just see 1, 1, the first, you can, sometimes you can see in the beginning, the first digit is 0, 0, 1, 1, and so on. Okay, you will see that pattern also. That is also okay. And you'll get the numbers, the terms of the sequence by adding the just previous digits. See, 1, 1, after that, how we'll get 2? You add 1 plus 1, 1, 1. You'll get 2. And how will you get 3? By adding 2 plus 1, just previous terms, previous numbers. Then how will you get 5? It is 3 plus 2, 5. Then 5 plus 3, 8. 8 plus 5, 13. So like that, you can form the Fibonacci sequence. And usually this Fibonacci sequence commonly denoted by Fn.
And Fibonacci sequence is always attractive and having many mathematical properties. They appear in geometry, algebra, number theory, and many other fields, even in nature. This sequence plays an important role in the study of arrangement of leaves, branches, flowers, or seeds in plants with main aim of highlighting existence of patterns. Now you can see the arrangement of leaves, and branches of a tree. See the picture. And it was Kepler who noted that on many types of trees, the leaves are aligned in a pattern that includes Fibonacci sequence. Look at the first small plant having 3 leaves. You can denote the first one as 0. That means we are starting from 0. And it's the alignment. It is towards the right. And when we are moving in a spiral form, in a particular manner, you can count 1. The second leaf was 1, and the third leaf was 2. Okay, so you are taking 1, 2, and you can see the same alignment in the leaf 2, the same alignment as in the leaf 0. 2 is a Fibonacci number, right? Now look at the next one, the next plant. The first leaf was denoted by 0, and after that the same alignment you can see in the 5th leaf. See, 5th leaf, after moving in a particular pattern, the same alignment you can see in the 5th leaf. It is a Fibonacci number. And look at the next plant. You can denote the first one as the 0th one. That means we are starting and orienting like this in upward direction. And in the 8th leaf, see the orientation, the same orientation what we have in the first one, the 0th one. 8 is a Fibonacci number. In most of the plants, you can see these types of arrangement exactly same as what Fibonacci sequence is. Okay, now, and similarly, this sequence you can see in the branches of trees. See the branches of trees? First we have 1. After that it is broken into, or it is divided into 2. After that 3, and this 5, 8, 13, 21, and so on. Everywhere you can see these types of arrangements. This is connected with the Fibonacci sequence. Now another beautiful example I will tell you. See the petals of flowers, how beautiful it is. You can see the petals of flowers. You might have seen flowers having one petal. See the white lily there, only one petal. And anthurium is also having only one petal. In the second picture, you can see it is actually having a flower having 2 petals. You might have seen euphorbia, that flower. And the flower having 3 petals, it is trilinium. And flower having 5 petals, we don't have 4 petal flower, 5 petals. And there may be 8 petals, 13, 21, 34, senior and all having 34 petals. See how these petals are arranged. See the beauty in nature, the beauty of Fibonacci sequence in nature, in flowers. Now, if we take a square according to Fibonacci sequence, you consider a square, Fibonacci in the form of Fibonacci sequence. Okay, 1 as the first number, so take a square having side 1. And then again 1, so next square, then 2, the next square having the side 2, then 5 having side 5. Like that, when you are considering squares, it may be called golden rectangle according to Fibonacci sequence. And when we are drawing the diagonal of each rectangle or each square. If you are joining the diagonals of these squares, we'll get a spiral. A spiral shape we'll get. And that spiral is called the Fibonacci spiral. The Fibonacci spiral. You can see this is the Fibonacci spiral or the golden spiral. There you can see 1, 1. See, I considered the square having 1 unit, then again 1 unit, the next square will be 2, the next square will be 3, then 5, 8, and so on. And when you're joining the diagonal and drawing in the form of a curve, not exactly the straight line segments, the diagonals, when you're joining this, you will get in the form of a spiral. And this spiral is called the Fibonacci spiral, which is very important and beautiful also. And we can see many spirals in the universe. Let us consider a few examples. The spiral galaxies. See the spiral galaxies? You have seen this picture so many times, I see. Which is called a logarithmic spiral, actually. Logarithmic spiral. And another important spiral we can see in the sunflower. You might have seen sunflower, right? See, in the middle portion, there are few seeds. It is arranged in a particular pattern. A beautiful flower. More than that, they are also mathematically marvel. And the spiral in the center seeds are generated from this sequence. In sunflower, the seeds are arranged in Fibonacci spiral of 21, 34, or 55. It has two series of curves winding in opposite direction. So we can see Fibonacci spirals in sunflower. The first picture, it contains, when you are counting this, the seeds in this first one, you can see it, the count is 34. Okay. And for another sunflower, it may be total seeds arranged in a spiral form, it will be 55. And the next one, you can see a total of 21 seeds are arranged. And these seeds are arranged in two spiral forms and winding in opposite directions. See the beauty of mathematics in nature? Now, see how beautiful the spiral is formed in a pineapple fruitlet. In the pineapple fruitlet. We are eating pineapples, right? But didn't see the beauty in it, isn't it? It is found that in majority of this pineapple, there is 8, 13, 21 rows of fruitlets. 8, 13, 21 rows of fruitlets. And in smaller ones, sometimes it contains 5, 8, and 13 in that order. You can see in the pink colored lines, when you are counting those, the fruitlets, you can see it may be in the order 8, 13, 21, Fibonacci numbers, and 5, 8, 13 in smaller ones. And it has 3 series of spirals derived from roughly hexagonal pattern of fruitlets. You can see that. See, when you are projecting this into the two-dimensional plane, you can see the hexagonal pattern there. Okay, the pattern of the fruitlets. So it has 3 series of spirals. Okay, now come to the next one. It is the sequence of shells. The sequence of shells. It is a very beautiful object. Here you can see the tendency of increasing in size but maintaining the same shape. The same spiral shape is existing but increasing in the size. There is another example. And why this? It's a framework of nature actually. The most efficient way to grow strong, stable structures. And another beautiful object is the starfish. The starfish. So look at the starfish. It displays the Fibonacci number 5. 5 is a Fibonacci number, right? So here you can see 5. Also, the pentagon shape made this a beautiful one. Again, in so many areas, you can see spirals. In waves, see the shape of the waves. In pine cone, you might have seen pine cones, the buds of trees, the sand dots, etc. Now comes the mathematical formula for beauty. So already we had seen the beautiful formula. Now comes the reverse. The formula for beauty. What is the mathematical formula for beauty? How do you measure beauty? We know beauty may vary, very well subjective, but there is thought to be mathematical reasoning behind why we are attracted to certain shapes and objects. And this is called the golden ratio. The golden ratio. Symbolized by the Greek letter phi. It is actually denoted by the Greek letter phi. And this has a constant value. Phi is equal to 1.618033 and so on. Now, how to find this golden ratio? Here you can see a line segment. The first one having in red colored, you can see the length as A, it is the larger one, and the other one B, the smaller one is B. So the total length will be A plus B, right? And you can calculate the golden ratio by taking A by B. A means the larger side divided by B, the smaller side. And that will be same as the total length A plus B divided by A. Total length A plus B divided by A. And if this ratio is 1.618 and so on, we'll say that this is the golden ratio. So this we can apply everywhere in order to say whether something is beautiful or not, or something should preserve this golden ratio or not. And when you are considering the Fibonacci numbers, you can see this Fibonacci numbers actually preserves this golden ratio. You take examples of that. See the pictures. The Fibonacci numbers, you take example. See, 2, we know 2, 3, 5, etc. The Fibonacci numbers, and take the ratio. You take 2 and 3. So 3 by 2, it is 1.5, nearly equal to our golden ratio. Next one pair, 3 and 5. So 5 by 3, it is 1.66. Then 8 by 5, it is 1.6. 13 by 8, it is 1.625. Then 13 and 21, when you are taking 21 divided by 13, it is 1.6153 and so on. And if you have some larger values, if you are considering 233 divided by 144, it is 1.6180555. Again, some more larger value, and when we are taking next to 377 divided by 233, it is 1.618025751 and so on. And this, you can see when you are taking any two adjacent Fibonacci sequence, you can see the golden ratio. And we already had seen that everywhere Fibonacci's sequences can be seen. So when you're connecting this with golden ratio, we can say that everywhere we can see this golden ratio. Okay, so golden ratio can be seen everywhere in the nature. Now, see, you can see golden ratio in DNA. Okay, we can discuss some biology. Golden ratio in DNA, how? So remarkably, it has also been observed in DNA, the golden ratio. The program for all life was based on this golden section. A DNA molecule measures 34 angstrom by 21 angstrom at each full cycle of the double helix spiral. And this ratio results in 1.61904, and which is close to 1.618. That means the golden ratio. Now you can check whether your face is beautiful or not. How? The golden ratio in face measurement. See how beautiful face I have. Okay. The golden ratio in face measurement. What do you have to do for that? You take two lengths. For that, you take the length of the face, the total length of the face and width, eye to eye width. Okay? Top to bottom, this length. The length of the face divided by the width of the face. Suppose you are getting it as 1.6. And this is for a beautiful face. That means a beautiful person's face is 1.5. That means 1.5 times longer than its width. We are all familiar with Da Vinci's the beautiful picture Mona Lisa, the wonderful painting. In this, we used a sequence with golden spirals which stems from the perfect rectangles. So you can see the large rectangle. Okay, large rectangle. After that, it is reducing. Okay. He created rectangles within the corresponding dimension 1.618 from each descending Fibonacci number in the order 8, 5, 3, 2, 1, etc. Now, we are very interested in photography, many of you, right? How to make your photographs more beautiful. I'll tell you the trick. The golden ratio in digital photography. You can see these two pictures. The first one containing, see so many flowers you can see, so many roses you can see. But look at the second picture. It is a cropped form, which is beautiful. Either the first one or the second one, which is more attractive to our eye. The second one, sure. There is golden ratio. Okay, in digital image editing, the software uses these types of golden ratio. In magazine and all, in order to become the picture as a beautiful one, they used the concept of this golden ratio in order to make the magazine more beautiful. You can also try this. And one important thing always you have to remember is, this does not make everyone with proportion close to this golden ratio have a perfect square or beautiful. Beauty is still in the eye of, not the phi of the beholder. Okay, now another question. Does the study of mathematics change our brain? Does the study of mathematics change our brain? Certainly. Mathematics is the food for our brain. The abstract and concrete thinking leads to the development of brain muscles. So study mathematics, the study of mathematics certainly increase your intelligence, no doubts. So practice and practice in order to increase your intelligence. Where I'm connecting to different cultural forms. The cultural forms, if you're taking, can we find mathematical beauty in culture? Mathematics and music. Mathematics and music. Are they connected? Yes, of course. When mathematics is included in music, there comes beauty. Music involves, all of you know, It is counting, rhythm, scale, pattern, symbols, tones, pitch, etc. These all are connected with the mathematics. And the sounds are broken into waves. We know the musical sounds in the picture itself, you can see it is given in the form of a wave, right? And each with a fixed frequency. And actually, the concept of fractions we are using in music. And these are all mathematical divisions of time actually. And talam is also very important. And when we are studying music, you can see different types of talams are there. Ati talam, 16 matras, and 5 types of jadis. So jadis in the sense, in the meaning is the different types of arrangements of numbers. For example, let me say, as I'm a classical dancer also, so I'll say something about jadis. So the first jadi, total 5 jadis are there. The first jadi is the Tisra jadi. Tisra jadi means takita, 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 takita 3, takita 3. So that beat is repeating and repeating. That means it is a Tisra jadi. And the next one is actually, there is 4 beats. It is Chaturasra. Chaturasra, it is actually Takadhimi, takadhimi. And this beat is repeating. Takadhimi, 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 takadhimi. So like that, it is Chaturasra. And we can see Ghanta jadi. Ghanta jadi, it contains 5 beats. Ghanta jadi is Taka, takita, taka, takita, taka, takita, taka, takita, taka, takita, taka, takita. So like that, when you are repeating, you will get Ghanta jadi. And the 4th one is Mishra Jati. Mishra Jati. Mishra Jati is 7 beats. That is actually Takita, Takadhimi. So when you're repeating this, we'll get Takita, Takadhimi, Takita, Takadhimi, Takita, Takadhimi, Takita, Takadhimi, like that. Okay, it involves 7 beats. And now comes the 5th one. The last one is the Sankirna Jadi. Sankirna Jadi, it contains 9 beats. It is Takadhimi, Taka, takita. So when you are repeating this, what will you get? Takadhimi, taka, takita, takadhimi, taka, takita, takadhimi, taka, takita, takadhimi, taka, takita, like that. So all these are related with the mathematics. Now, what about maths and dance? There comes happiness, right? See, dance requires, first of all, music, the shapes, the movements, the symmetry. See, dance is constantly counting, as I said earlier, counting their steps in order to keep time with music. They form angles. Here itself, you can see the ankles, the lines, the shapes with their arms and the legs. They keep the symmetry of our body. Our body is symmetrical. Okay? A representation of symmetry. And this helps the dancers to balance their body. Now, what about mathematics and art? Mathematics and art. You can see the different beautiful pictures and the mixing of colors in ratios and proportions. And this combination makes all these pictures so beautiful. And you can see the different geometrical shapes also here. And another important concept, a beautiful thing that we can see in the nature itself is the concept of fractals. The concept of fractals. The concept of fractals means a particular pattern is repeating so many times. You can see a fractal in the first picture, and when you're minimizing, taking a small miniature of this, you can see a sort of fractal, and that shape is repeating. And the second picture, you can see the first picture, it is the miniature. When you're repeating the same pattern more and more time, you'll get the last picture. So like that, the important, beautiful patterns, fractals, you can see everywhere. And another sort of shape we can see in while making origami. What is origami? Origami, it is a Japanese craft. As most of your students, you might have learned origami. You know how to make these types of objects, the 3D objects. See, by folding papers, we can create wonderful 3D shapes. And when you are unfolding this paper, you can see different types of patterns in the form of triangles or in the form of squares, etc. And when you're seeing in most of these triangles, it may be congruent also. Okay. Now, finally, I'm giving you some beautiful pictures showing the symmetry. The symmetry. See those pictures? How the God created all these things by by using the rule of mathematics. So I wondered whether God has created mathematics or we created mathematics. See the beautiful pictures, all are symmetrical. When you are taking a perpendicular an axis, you can see the mirror images in these beautiful pictures. You can see different patterns also. The different patterns. See the different patterns? The beautiful lines. The second one in the form of a 3D object and different patterns also. And the different shapes, the constructions, the different constructions. So there you can see some sort of geometrical series and all. The different constructions. This is a China Gate and Burj Khalifa and bridges and so on. You can see the application of mathematics, the beauty of mathematics. So in sight of the current issue, we know so many people are suffering from the pandemic. Okay, so in the current issues such as vaccines, gene therapy and global warming, etc., both mathematics and science students have a vital role to play, whether it is developing new solutions or contributing to make the planet a better place to live. Mathematical beauty you can see everywhere in the universe. Thank you very much.